organizers for organizing such a nice conference in such a nice place. And this work was done, the second part of the work was mainly done by Olga Sulimenko from Kiev. She is a graduating graduate student, and she's looking for a job. So people who, experimentalists who want a good theorist in antiferromagnets, remember this name. And what I will be talking about is the following. We know very well that there is a technological problem of a terahertz gap. It is rather easy to generate everything, almost everything above 10 to the 13 hertz. We have plenty of lasers here. We have plenty of generators and oscillators in the lower region, but around the terahertz 10 to the 12, it is really difficult to generate monochromatic tunable signals. There are means to generate continuum pulses, but tunable monochromatic terahertz signals are in short supply, but they are needed for maybe for the FG communication, 5G communication, for non-invasive control and imaging, and for atmosphere probing. And the industry wants generators in terahertz, but they have a very harsh requirement. Requirements are that these devices should be small. They should not have a bias magnetic field, because industry hates bias magnetic field for two reasons. They do not like to have magnet at all, and when they have magnet, the magnet is not thermally stable. So no magnetic field, it should be tunable. And what to do? Let us look at what are the eigenfrequencies in ferromagnets and antiferromagnets. And our idea is to use antiferromagnets as an active medium for generation of terahertz, and it's simply because the ferromagnetic resonance frequency is proportional to the external field and dipolar field, which are dependent on the shape of the sample, while in antiferromagnets we have weak anisotropy and huge internal exchange field, about 1000 Tesla, which actually keeps the antiferromagnetic sublattices antiparallel to each other. So we have a huge internal source of stiffness. If we can tap into that, then easily, without any bias magnetic field, we can get to the frequencies which are substantially higher than frequencies which are achievable in FMR, where you cannot really create external fields in a portable device more than even 1/3 of a Tesla. This effect, which you see here, is called the exchange amplification. Everything inside the antiferromagnet is multiplied by this huge exchange field. And so, for example, a rather small anisotropy field in antiferromagnet is amplified by the exchange. And so the eigenfrequency in antiferromagnet, as I said, could be between 0.5 tera to several terahertz. Traditionally, in ferromagnets, if we want to create generation, we have spin torque or spin Hall oscillators. What do? One way or the other, we create spin current, which is parallel to the static direction of magnetization. And this spin current creates a spin transfer torque, which with the proper orientation of the polarization creates negative damping, which compensates natural damping in the ferromagnet, and we get generation. The similar approach in antiferromagnet will not work at all, because we have two antiparallel sublattices, and the spin transfer torque, which creates negative damping for one of them, creates positive damping for the other. As a result of that, then no result will be achieved if we direct polarization along the Néel vector or along the static orientation of the sublattices. However, if you apply the spin current with polarization perpendicular to the nail vector, this spin torque will actually work as a field. What it will try to do, it will cant the sublattices. And as soon as sublattices are canted, they will immediately be in the huge internal field of the antiferromagnet, and there will be a torque exerted by the exchange field on the canted sublattices. So we cant them by the polarized current or spin current, and then they start to rotate in the internal exchange field, and the frequency of this rotation is proportional to this HIFM, which is exchange field multiplied by the canting angle. And the canting angle could be small, because we cannot afford to have too strong a current. But since the multiplier is so large, we can easily get to half or 1 terahertz with a reasonable current density. The green arrow is the torque which acts on the canted sublattices from the internal exchange field. All right, now we found, at least on paper, the way how to rotate these sublattices, how to excite the magnetization dynamics with high frequency. But how to get it out? Well, yeah. But when they rotate, they actually create a spin pumping back into the platinum, into the layer where the initial current was flowing. And if we take the work of Gerrit, Yaroslav, Bratas, and all the classics in the spin-dependent transport, we'll immediately find that this current induced in platinum is actually proportional to the derivative of the rotation angle. And here the story ends. If the rotation is uniform, the only thing I will get is the uniform current, which is not interesting, independently of what is the frequency of the rotation. The frequency of the rotation will only determine the magnitude of this current, that's all. So we need something else. Actually, this idea about rotation in the internal field is not mine. This idea was fully formulated by Elena Gomanai and Loktiv about 5 or 6 years ago. So our contribution to all this was the following. We realized that there are antiferromagnets like nickel oxide, which inside the easy plane, they have a weak perpendicular anisotropy, which actually determines the lowest antiferromagnetic resonance frequency in nickel oxide. And because of this anisotropy, the trajectory of rotation is not plane. The situation like in the case of the parallel pumping in ferromagnets. This trajectory is not plane. As a result of that, the Z component of magnetization will change twice faster than the rotation frequency. And what you will get, you get a rotation with the changing angular velocity. As a result of that, in spin pumping, you will get the signal with a frequency twice larger than the frequency of rotation. Actually, very recently, it was found experimentally in this work by Wadley and collaborators that if your antiferromagnet is conductive, then you can create a tunneling junction and you can extract the magnetization dynamics from antiferromagnet in the same way as from ferromagnet. But that will not work for nickel oxide or hematite. You need something conductive. And so the candidate for such conductive antiferromagnets, which are good for generation, is the manganite gold. To describe the motion of these two sublattices, we write a standard two equations, Landau-Lifshitz equations, where this is damping, this is spin torque created by external spin current, and the internal field includes a huge exchange field and two anisotropy fields. One anisotropy field which keeps magnetization in the easy plane, and a weak perpendicular anisotropy which creates this non-plane trajectory of rotation. And if you switch from these two equations to a sigma model and replace difference in magnetizations by the Néel vector, you will get a surprisingly simple equation for the rotation of a Néel vector, which is just a physical pendulum, basically, where the gravitational acceleration is replaced by this perpendicular anisotropy, damping is replaced by Gilbert Dumping, and mass is replaced by inverse of the exchange field. And this equation can be solved, and you will get that phi dot, the derivative of the rotation angle, will have a constant term, and will have a term which is rotating, which is oscillating with a frequency twice larger than the Larmor frequency of rotation, which is proportional to the Canting angle and therefore to the current density. And when you calculate the frequencies you can achieve in nickel oxide, you will see that these frequencies are reasonable. You can get to 1 terahertz at the current density of about 3 to 10 to the 8th ampere per square centimeters, which is has been achieved in ferromagnets easily. But we have, and the signal which you can get, electric field, is also reasonable. It's about volt per centimeter, but you see we have a terrible problem. With the increase of frequency, the amplitude you can get through the spin pumping back in platinum is actually decreasing. So if we are extracting signal that way, we should not expect a good generator at large terahertz frequencies. So we need to invent something else. But before I will show you the new part about the invention of something else, I would like to notice that the equation which describes the dynamics of this antiferromagnetic generator is absolutely 100% equivalent to the equation describing the generator on the Josephson junction. So basically this device will repeat at room temperature the dynamics of the Josephson junction generator, which is happening at 4K.
Current biased, right?
Yeah, current biased. Of course, current biased. I mean, there's driving term here. All right. So the motion of a particle in the washboard potential, or the motion of the physical pendulum in the gravitational field of the Earth driven by the external force, is very well known. And we know that there are two thresholds here. One threshold is to overcome the potential barrier and to put the system in motion, and another threshold is to overcome the friction. And if you start here from a large current density, as soon as you overcome the threshold of generation, you can drastically reduce the current density. You'll get a lower frequency, but the device will continue to operate. This is very important for the applications, because you see this is 100 nanoseconds. So the device will survive for 100 nanoseconds high current density, and after that you can reduce it twice. Yes, it's picosec. Yeah, it's it's very short. Yeah, you're absolutely right. 100 picoseconds, 1/10 of a nanosecond. We calculated with Vasil the generation line width using our standard approach, and the result is very encouraging. the generation line width of this device at 1 terahertz would be about 0.3 megahertz, which means that expected Q factor is 1 million. Even if we make a mistake here of 100 times, still the Q factor of 10,000 is quite acceptable for real applications. And you've seen that the device would not need magnetic field and can work at current densities of about 10 to the 8th ampere per square centimeter.
This is assuming that the Gilbert dumping always stays. This is a Gilbert dumping.
You see, Gilbert dumping here it's here, and the Gilbert dumping which was put in this calculation is a Gilbert dumping with the account for spin pumping. So we take into account the fact that when we put platinum on the antiferromagnet, we spoil it. So we are calculating like engineers, not like real theorists. Another interesting property of this device is the following. Imagine now that I will supply on this device a signal which is a combination of the DC signal and a sinusoidal signal of a given frequency. And I will arrange the magnitudes of a DC signal and this signal in such a way that J0 is below threshold, while J0 plus Jm is above threshold. So the threshold of generation is exceeded only during one small part of a period. We did numerical simulations in the equations which I've shown you. If we supply the signal of a gigahertz frequency, we get with this clock frequency generation of short pulses, but the duration of a short pulse is antiferromagnet. This duration has nothing to do with the duration of the external signal. It is determined by the internal properties of the antiferromagnet, basically by the lowest antiferromagnetic frequency inverse. What's this? This is an artificial neuron working with a clock frequency of several gigahertz or several tens of gigahertz, producing the spikes, neuron spikes, of the duration of several tens of picoseconds. So if you can realize that, you will get a neuromorphic computing with really high speeds. If people who will come to Intermag in Singapore, there I will bring an invited talk where I will discuss the practical implications of this, the logic using this kind of devices. All right, but I said we have a problem. We cannot really go with frequency higher than half a tera because our amplitude, due to the extraction through the spin pumping, will decrease with the increase of frequency. Let us take a different material. Let us take a material which a part of everything else will also have a DMI. This material is very simple. It's a hematite. DMI does one thing. If this is an easy plane, it cans the magnetizations in the easy plane, so your hematite becomes a weak ferromagnet. So there is a net DMI-induced magnetization in easy plane. Now, if I apply the spin current perpendicular to the easy plane, this whole structure will be lifted out of the easy plane and will start to rotate in this exchange field. But now we have a net magnetization vector which is rotating with sublattices. This net magnetization vector, which is rotating with the Larmor frequency, is nothing else as a magnetic dipole. And actually, we measured, we can actually afford to have IFM thickness, which is not very low. We can go to 25 nanometers easily, and that will not substantially reduce frequency, and that will allow us to change the effective damping in the material. And if we will take the usual emission model, when you have a magnetization vector rotating, it's equivalent to two perpendicular dipoles. And if you simply take Jackson, and whoever passed the PhD exams should remember these formulas by heart to the end. And we can calculate the excitation of a microwave resonator by this two magnetic dipoles. And we got the result. This is the power which is produced by this rotating dipole, mdmi. You see it's proportional to mdmi squared, the volume of the antiferromagnet, and proportional to frequency. Now it's increasing with frequency. And you also, if you put it in a good resonator, you can multiply this power by the Q factor of a resonator. And so we did the calculations. Olga Sulimenko actually did it for the free space. She did its calculation for the rectangular cavity. But the punchline is that he did it for a dielectric resonator. And if I plot all this, you can see that if I use a good dielectric resonator, then I can get a microwatt of power at 1 terahertz. That's exactly what our industry wants. No bias field, tunable by current, 1 microwatt at 1 terahertz. Everything looks good on paper. Now it's a challenge to the experimentalists, and first of all, the challenge to technologists. What we need a monocrystalline antiferromagnet which is grown in such a way that easy plane is perpendicular to the interface. Because the spin polarization is created, whether it's spin Hall or spin torque, in the plane of interface, we need the spin polarization to be perpendicular to the easy plane. It's as simple as that. We did the calculations. If the misalignment is up to 30 degrees, everything will work, at least in numerical simulations. So I gave you the numbers, I gave you the orientation. Let's try to do it. We got a grant from NSF with Ilya Krivorotov, and we are desperately trying to do this practically. But I told you all the secrets, so we want competition. We want somebody to do it as soon as possible. Thank you for your attention.